All right, so in the previous video, we talked about these winding resistances R1 and R2. Basically, we're looking at the same circuit here, but it's an important concept in electrical engineering, this concept of input impedance for any circuit, really. It basically is the impedance that the source that we care about in our circuit, the impedance that that source is going to see in the circuit. Of course, I don't mean see in a literal sense. It can't see anything. But what it means is what is the effective impedance that we're presenting to that source, okay? So if I have, some voltage source, Vs, and I connect, let's just say I have a 10-volt voltage source, and I connect some kind of impedance here, Z, or let's just let it be an R. So let's just say that we're going to operate in DC for the sake of example. I present some R here, and I know that this is 10 volts, and then I measure the current flowing here, and I get 10 milliamps. Then I know that I must have connected a 1 kilo ohm resistor to this circuit, right? Because 10 volts over 1K gives me that 10 milliamps, right? That's basically telling me I know what resistance I connected here. But what if I had a more complicated circuit? What if I had a circuit that I connected a 10-volt voltage source into something much larger, some big network of a whole bunch of components, but I still measure the current here and I still get 10 milliamps from a 10-volt voltage source? Well, I definitely didn't connect a 1 kilo ohm resistor necessarily, sorry for stumbling there. But what I noticed is that I effectively connected a 1 kilo ohm resistor here, even if it's not a 1 kilo ohm resistor. It might be some big complicated op-amp circuit or something, but it still pulls 10 milliamps. So what we would say is not that we connected a 1 kilo ohm resistor, but rather that the input impedance or the input resistance of this circuit is 1 kilo ohm, because that's effectively what the source is seeing, as if that resistance were 1 kilo ohm. And that's what we're interested in here. What is the effective impedance that the circuit is going to see for this big transformer? And so we can basically determine that by finding, this ratio here, the voltage to the current that's drawn from the battery. So in this case, I've got Vs and I've got a current I1. So if we can determine the ratio of Vs over I1, then we can find our input impedance for this circuit. And that's going to be another exercise in using the dot convention, drawing this equivalent circuit, and then finding Vs over I1. So let's go ahead and just do it. If this video gets too long, I'll have no problem just making another one, part 2 for this. So that's going to be Vs. Of course, we're going to get an impedance of R1 for that resistor. We're going to get J omega L1 for that inductor, and then we're going to have an induced voltage source here. I'm running into my UNLV logo there. Just draw the wire interestingly. Why not? Why not be different here? And this is going to be of size J omega M, and it's going to be induced by I2 from the other loop. And then for this one, it's going to be J omega L2, a resistance R2, a load impedance ZL, and of course an induced voltage that's going to be J omega M multiplied by I1 because it's induced by I1. Okay, the polarity here, if I look at the dot convention, this is the same convention we've seen over and over now. I1 is flowing into the dot here. It's going to push a current out of the dot here. So my polarity of this source here should be plus to minus in this direction. I2 is out of the dot here, which forces a current into the dot here. So if I want current flowing in that direction in the circuit, I need this polarity for this source. And now, of course, I'm ready to solve. I can go ahead and write my pluses and minuses in these circuits. I2, plus minus, plus minus, plus minus. And I need to write two equations here. One for the first loop. We'll go Vs minus I1 times, and then there's a couple of impedances there, R1 plus J omega L1. And then I have a plus J omega M times I2, and that whole thing is equal to 0. So that's my first equation. Second equation, I'll just start here and go this way. J omega M times I1. And I've got minus I2 times this sum of these impedances, R2 j omega L2 ZL, that's going to be equal to 0. So those are my two equations, and now I basically need to go through and solve this thing for Vs over I1. Basically, my best course of action here is going to be to solve for I2 in terms of I1, plug that in here, and then divide out I1 from both of those terms. So let's go ahead and do that. So I get j omega, I could actually just rewrite this whole entire expression by setting them equal to each other, just like that. And now I can say that I2 is basically going to be equal to j omega m divided by R2 plus j omega L2 plus ZL multiplied by I1. All right, and now this needs to get plugged back into, oh, I wanted to solve for I1, didn't I? I did want to solve for I1. Okay, let's just rewrite this. I1, is that right? Did I want to solve for I1? No, I wanted to solve for I2 because I'm going to plug in I2 here. Yeah, I had it right. Okay, good. I just didn't write I1 here, so that's why I got confused. Or maybe I did. I don't know. Anyways, this is correct. I think this video has gotten a little bit long, so in the next video I'll wrap up this derivation of the input impedance of this transformer. And yeah, we'll just wrap up the algebra. Should be pretty straightforward. Just going to be a matter of plugging this thing in to I2 here and then solving for this ratio Vs over I1. All right, so we'll see you guys in the next video.